Hello, my name's Martin Unwin, and I'll be talking today about the flight of a new miniaturized and integrated Spaceborne GNSS receiver. I'd like to acknowledge my co-authors, Reynold de Vos van Steenbeek, Andy Porfelman, Simon Miles, and Jonathan Rawlinson from Surrey Satellite Technology Limited. Moving on to the next slide. So needs arising from space for Spaceborne GNSS. Future satellites are going to continue in the trend of getting small in the new space scheme of things. Very small satellites may still have a need for synchronizing clocks and locating the satellite. For example, from a need from the AOCS system and from the payload to know where the satellite is and what the time is. GNSS receivers may be in different form factors, but they might include the CubeSat PC104, or they may be smaller than that. Receivers have to be low power if you need them to operate continuously, otherwise they could be intermittently operated to lower the power. There are some applications which will benefit from dual GNSS antenna. So, for example, if a satellite's not pointing at the Earth, it's an inertial application, then you always have an antenna that is a good view of space. There's an increasing need for, as well as GPS, Galileo signals, GLONASS and Beidou, and there are different reasons for this, some technical, but sometimes there's national and political reasons as well. There may be a need for special, precise timing. For example, a disciplined oscillator on the output to provide more precise time. And there may be a requirement for very precise orbit recovery afterwards. Or alternatively, recovery on board itself. And in order to do this in real time, you need to use precise point positioning, which requires a data channel to correct the ephemeris and clocks. And there's also an increasing need for GNSS for remote sensing, for example, GNSS reflectometry and radio occultation. Surrey Satellite Technology Limited has a long history with space receivers, and it was an early adopter of GPS receivers for small satellites, and it's the first use of GPS on microsatellites on POSat-1 in 1993 in collaboration with Portugal. And there was an early use of GPS on a very small satellite. SNAP-1 was launched in 2000, and that was a 7-kilogram satellite, pre-CubeSat standards. And the GPS receiver was used for autonomous maneuvering to chase after another satellite. And then there's the ESA Proba-1 satellite that was launched in 2001, and that has SSGL's SGL-10, and it is still in use now in orbit. SSGL developed a range of space GNSS receivers for SSGL satellites, first and foremost, but also for customers across the world, including a wide range of customers, such as ESA, NASA, US Air Force, JAXA, and so on. And SSGL achieved the first position fix outside the GPS constellation on a demonstrator that was carried on GOVA, the forerunner of the Galileo satellites. There's 3 examples of the GNSS receivers that SSGL has produced in the past: the SGL-10, the SGL-5U, and the SGL-7. This talk is looking at a new GNSS receiver that's that's been designed to address 2 applications, 2 particular missions in particular. So Vesta-1 is a CubeSat, and that required a GNSS receiver. And so that was one driver. But there was also a perceived need for a GNSS receiver that would fit into SSGL's integrated avionics suite, which was called the Core DHS. And so the same receiver was used to develop these 2 products, the SGL LEGO standalone and the SGL LEGO combined, integrated it onto the Core DHS. And the features that it's low cost, low power, It supports GPS, GLONASS, Galileo, and potentially Beidou for the future, and it has 2 front ends. So just a few more details about the SGL LIGO. It's COTS-based technology, and the correlators are embedded in flash FPGA. So that means it's a very low power processor. It's in a PC104 CubeSat format. Now that means that it should be possible to plug it together with any CubeSat, and it should still work, but our experience is that the standard is not that simple, and so we have to have some configurability so that you plug it in, it will connect properly. So we do have some configurability on the board. We can change some links to allow for different satellites. And there's a datasheet on the SSGL website. There's a list of specs here. Maybe I will not read this out, but because one of the luxuries of a presentation is that you can pause it and have a look yourself, or go and look at the website datasheet. A few more of those details. That in its lowest power configuration, the SGL LIGO only takes 0.5 watts continuous. The LNAs in front end allow the use of passive antennas, and intermittent operation can lower the power even further. It can do GPS, GPS and GLONASS, or GPS and Galileo. It can't do all 3 at once. It has dual front ends. This supports inertial satellites, but not if it's in the GPS and GLONASS configuration. In this case, it needs those 2 front ends to support GPS and GLONASS respectively, so that you only have 1 antenna that supplies the 2 front ends. In terms of radiation tolerance, it has EDAC protection and watchdog to give it robustness. There hasn't been a full unit total ionization dose test, but the assumption is that it's at least good to 5 kilorads, probably more but we can't say that until it's been tested. This is adequate for most small missions, but for higher altitude, high rel missions, we expect there'll be a need to undertake further testing. And there's a picture of there with the SGL LIGO with the radiation shield on. Vesta 1 is a CubeSat. It was designed for a rapid demonstration of the VDES, VHF data exchange system, SSGL working with Honeywell. It's a 4 kilogram 3U 3-axis stabilized mission. It has magnetorquers, 1 wheel, 1 sun sensor, and the SGL LIGO is integrated into the stack. The lowest power configuration was used, so no external LNA. It's 1 antenna. It's a bare antenna to give the smallest, snuggest fit in the envelope. It's low power, but and what that means is that it has slightly lower signal to noise ratio, so there's a little less margin for external interferers, but this is the way it was designed, and it works well. The Vesta 1 launch was on a Falcon SSOA small sat express launch from Vandenberg Air Force Base on the 3rd of December 2018. On that mission, it had deployed no fewer than 65 satellites, of which 45 were CubeSats. And there's a link here for a YouTube animation that gives you an idea of how it spits out all these different satellites, and CubeSats and larger satellites. And when it was launched in orbit, the tracking elements were issued by NORAD, North American Air Defense. And a common problem is that it's easy for them to misidentify targets because there's so many of these satellites that come out. And then they issue the tracking data for the wrong satellite. It's understandable why this would happen. And what we found when we first started communicating with Vesta is we did communicate, but it was patchy and unreliable communications, especially when it goes straight overhead. We've got the fastest acceleration rate. So there was a decision made to try and improve the communication link to initiate an early operation of the SGL LIGO earlier than expected. And it was operated, and even though the satellite wasn't completely under control in terms of its attitude, it was still tumbling the receiver managed to acquire and track signals, and it was able to generate the position fix and download that to the ground. And from that, we were able to identify the correct satellite from the others in the different two-line element sets. This gave us better elements, and it gave us faster acquisition of the satellite. The receiver itself tracked 8 to 12 GPS satellites, and it averaged 0.5 watts. And it identified which elements, so we didn't have any problems with tracking since. Since then, the mission has more or less completed with its main mission, but the SGL LIGO continues to be exercised after the end of the mission activities to gain heritage. The next mission is Astroscale's ELSA-D project. This is a mission that addresses clean spaces, demonstrating with a servicer and client satellites the technologies involved in chasing and docking in order to remove expired satellites. So Astroscale designed the services satellite, and SSGL designed the client satellite. The SGL LIGO was used in the ELSA-D client target satellite. And there's a picture there of the satellite with one of the antennas highlighted with the white arrow. This one uses the dual antennas, whereas Vesta 1 only used one antenna. So the dual antennas allow for the fact that it may be in a different orientation. The antenna may not always be pointing at space, but you have the other antenna as well. This satellite was launched just this year, the 23rd of March 2021, from the Soyuz from Baikonur. On this launcher, there were 34 satellites, 24 of which were CubeSats. The ELSA-D project is not SSGL's mission, it's Astroscale's, but it's enough to say that the SGL LIGO again helped in the early satellite identification. A similar story with Vesta 1. It was operated early and helped identify which satellite was which. And the ELSA-D mission is ongoing. The core DHS architecture is a suite of avionics that's going to be used in all future SSTL missions. And there was a requirement to integrate the GNSS receiver into this one board. So we have one board that has most of the internals of a satellite just in one place. It contains an onboard computer, attitude interface module, TTC receiver and transmitter, the SGL LIGO GNSS receiver, the zinc payload processor, and power supplies, which can either be configured from 12 volts or 28 volts. The SGL LIGO is integrated within this. In addition to that, there was a data connection added from the SGL LIGO to the zinc data processing, payload processing unit via the OBC. The first flight of the core DHS was on the DOT-1 small satellite. This is an 18-kilogram microsatellite. And this was launched on the 5th of July, 2019, on a Soyuz 2 with 33 other satellites. The main payload is the core DHS itself, but it did also have a Raspberry Pi with a 4K video camera. And if you want to, you can look it up on YouTube. There's videos that play, but there's an image here from the camera, an image of the Mediterranean. But it also records a video as well as an image. It also had a radiation monitor. And it was the SGL LIGO has been operating successfully as a GPS receiver using the first front end. Interestingly, the second front end was connected on DOT-1 to an 8 dBi left-hand circular antenna pointing down at the Earth in order to demonstrate reflectometry. The reflectometry is supported because it has the dual antenna. The SGL LIGO itself has dual antenna, but it doesn't have the reflectometry processing capability on board it. So there was an ESA study that provided support for the reflectometry implementation. This was implemented on the zinc. So which can be reprogrammed in orbit. It's a RAM-based FPGA and processor. The sample data from the SGL LIGO was piped to the Zinc, which was then reprogrammed to implement GNSS reflectometry. That project has been ongoing and it's been successful, and now DOT1 is collecting data from both GPS and Galileo reflections. This requires the SGL LIGO to be up and running and also the Zinc. And there's a picture here showing the typical results we're getting from Galileo and GPS delayed Doppler maps. And there's one example of the Galileo delayed Doppler map over the ice, where over the ice you get very strong reflection. It's quite clear. You see the multiple correlation peaks due to the Galileo modulation structure. SSGL is working closely with the National Oceanography Centre, working on the inversion of ocean wind speed from these delayed Doppler maps. So it's possible to measure the wind speed across the ocean using this payload. On a similar subject, slightly off course, is this mission called Scout 2 HydroNSS. This is an ESA Scout mission. It's a 3-year mission from kickoff to launch, and the budget for Scout missions is less than 30 million euros. So HydroNSS is a small satellite that uses GNSS reflectometry to measure 4 essential climate variables to do with hydrology. Those are soil moisture, inundation, freeze-thaw, and biomass. And it's using new technologies such as the dual frequency, that's L1 and L5, dual polarization, that's left and right, and circular polarization, and a new coherent channel that provides potentially higher resolution measurements of these coherent components of the reflections. And this project is building on DOT1 technology. There's a short video about HydroNSS. Again, if you search on YouTube and look up HydroNSS, you'll find it. So to conclude this presentation, we've talked about the SGL LIGO, which is a low-power, compact GNSS receiver. It's available as a standalone unit, which is suitable for CubeSats and other satellites, but it's also integrated into the avionics, which is expected to be used in larger missions. And it's been used in orbit on Vesta 1 and ELSA-D as the standalone configuration. And the most practical new contribution is that it's assisted in the early identification of the satellite within the crowd of CubeSats that's typically launched from these launches these days. When a satellite is deployed, it is a very nerve-wracking time, and if you have the wrong orbital elements, that can make things more frustrating. And this is one particular tangible way that the GNSS receiver can help quickly. And beyond that, it acts like a normal GNSS receiver. It continues to operate on both, providing position, velocity, and time to those missions. The receiver has been used in the DOT1 integrated in core DHS. It's been demonstrated, so it's now been designed into many other future missions. So for example, there's a picture here of Theos 2, low resolution satellite that's being built for and with Thailand, and that contains a core DHS which has the SGL LIGO, and that is going to be launched, I believe, next year. And the work on the SGL LIGO has also enabled GNSS reflectometry, in particular on the DOT1 mission, which is demonstrating this. And that is a stepping stone towards the ESA HydroNSS mission, which is using GNSS reflections to measure climate variables. And that's the end of the presentation. Thank you very much.